Hey, welcome back. Now that we have a basic grasp of limits, it's time to tackle one of the first big questions of calculus. Is it possible to find slope at a single point? At first, it might sound impossible. However, with something called the derivative, we can accomplish just that. To illustrate what the derivative is and how it works, I want you to take a look at the graph right here. I've got two x values singled out. This one, which we'll call x, and another one some distance away, which we'll call x plus h. And what I want to do is I want to find the slope connecting these 2 points on the graph. So to find the slope of this line, I'm going to use my slope formula, y2 minus y1 over x2 minus x1. So I found the slope of this blue line, f of x plus h minus f of x over h. Now before I go any further, I'm going to talk real quick about this idea called local linearity. Local linearity is the idea that if you take any point on any graph and you zoom in far enough, if you zoom in on that point, it's going to look like a straight line. So I want you to imagine if we zoomed in on that point, what would be the slope that we would see? Okay? Is the slope of this blue line equal to the slope that we would get if we zoomed in on the point x comma f of x? No, it's not really that close. Well, how do I get a better approximation? What if h, the distance between these 2 points, was smaller? Now this is looking better. I can see that the closer that these 2 points get together, the better of an estimate the slope becomes to the slope at a point at the point x comma f of x. So the distance between them, h, needs to get smaller and smaller and smaller and smaller and smaller, infinitely close to 0. So do we have a tool that allows us to take one value and take it infinitely close to another? Limits. So I'm going to take this slope formula that I found and apply a limit to make h as small as possible. And so this formula, the limit as h goes to 0 of f of x plus h minus f of x over h, is what we call the limit definition of the derivative. The way this works is for any x value that you plug in, the derivative will tell you what the slope is at that point. Meaning if you were to zoom in on that point, what would be the slope of the line you see? Or another way to phrase that is the slope of the tangent line at that point. So what we've got here on the top, this is the limit definition of derivative, which we just found together. Okay. One thing I want to point out is that the way you denote the derivative is like this. You read that f prime of x. So that little apostrophe, you're going to say prime when you read that out loud. What we've got beneath it, this is what we call the limit definition of derivative at a point. So if you want to know the slope, say, exactly at x equals 2, you can use this bottom equation. If you want to know the slope at any x value, you're going to use the top equation. So let's put it to work. Let's find our first derivative. Example 1, using the limit definition of derivative, find f prime of x for f of x equals 4x minus 1. Well, since this is our first one, let's start off by writing the formula. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Now that we've got our formula, it's time to start plugging in pieces. F of x plus h just means take your function, and everywhere you have an x, plug in an x plus h. So my next step looks like this. I've got the limit as h approaches 0 of f of x plus h, that's going to be 4 times x plus h minus 1, minus f of x, so minus 4x minus 1, all over h. And if you can do this step, going from the formula to plugging things in, that's probably the hardest step of the whole problem. At this point, I'm going to combine like terms, I'm going to clean things up and finish out this limit. So my next step is going to be the limit as h approaches 0 of 4x plus 4h minus 1 minus 4x plus 1 all over h. And then we're going to start canceling things out. 4x minus 4x minus 1 plus 1. That brings me to the limit as h approaches 0 of 4h over h. Notice those h's are going to cancel out. And so the value of this limit is 4. So what does that mean? The derivative of the function 4x minus 1 is 4. Well, if you think about the graph, what does 4x minus 1 look like? It's a linear function with a slope of 4. So no matter which point on the graph that I pick, the slope is 4 no matter what. So that's why f prime of x is 4. And what you'll find is any linear function has a constant derivative for exactly that reason. All right, example 2. Using the limit definition of derivative, find the derivative of g of x equals x squared plus 2x minus 1 Then, using the derivative, find g prime of 3. Okay, let's break this down into 2 steps. First of all, let's just find g prime of x. Let's find the derivative. So here we go. Using my formula, g prime of x is the limit as h approaches 0 of f of x plus h. That's going to be x plus h squared plus 2x plus h minus 1 minus f of x, x squared plus 2x minus 1, all over h. Okay? And again, once you get to this step, we just need to clean up a little bit. Combine like terms, cancel out anything you can. And what I notice once I get to this step is that after combining like terms, in the numerator, every term has an h. And so by factoring that h out, I can cancel the h in the denominator. And finally, with direct substitution, I can plug in 0 for h and get my derivative, 2x plus 2. So that's the long step. Find the derivative of g of x. The next part said find g prime of 3. Well, that's comparatively easy. To find g prime of 3, I'm just going to plug 3 into my derivative. 2 times 3 is 6, plus 2 is 8. Example 3 says, using the limit definition of derivative at a point, find g prime of 2. So same function as up above, but we're going to use the other definition from earlier. So g prime of 2 is the limit as x approaches 2 of g of x minus g of 2 over x minus 2. And again, I'm going to substitute. I'm going to combine like terms, cancel anything I can. It looks kind of like this. After combining like terms and factoring, I see that my x minus 2 factors are going to cancel. So I'm going to cancel those and plug 2 into x plus 4, giving me my answer, 6. Before we move on, I want to point out real quick that this method is fine and good. However, if you've already found the derivative, like we did in example 2, I could just plug into 2 times 2 is 4 plus 2 is 6. So don't do all that work if you don't have to. Example 4, given y equals x squared plus 2, find the equation of the tangent line at the point 2, 6. Okay, word association. From now on until forever, when you hear equation of the tangent line, just like that, you got to think of 2 words, point and slope. Because anytime we're going to find the equation of a line in this class, we need to know the point and the slope. Now, fortunately, the point was already given to us. The point that this line goes through is 2, 6. To find the slope, what we need is the slope at that point. Okay, and that's another key phrase. Slope at a point should trigger in your head derivative. So I need to find the derivative of this function so that I can find the slope when x is 2. So to find the derivative, I'm going to use my limit definition of derivative up above. And then through simplifying, combining like terms, canceling, and plugging in, we get the derivative y prime is 2x. So to find the slope at my point, 2, 6, I'm going to take the x value of my point, plug it into my derivative. So my slope is going to be 2 times x, 2 times 2 is 4. And once you have your point and your slope, you're going to plug those in to point slope form. Y minus y1 equals m times x minus x1, for those of you who forgot. So plugging in my information, I've got y minus 6 equals 4 times x minus 2. Now, depending on the type of question you're dealing with, you might need to simplify this. You might need to get y by itself, but with no further instructions, it is okay to leave just like that. In example 5, we're asked to find the equation of the line tangent to y equals x squared plus 2 at the point where x equals negative 3. So I see equation of the line tangent to, so I'm immediately thinking I need point and slope, and I want to point out that this equation, y equals x squared plus 2, is the same one that we had in example 4. So we already know the derivative, y prime, is equal to 2x. So how am I going to find my point? All they gave me was an x value. Well, to find your point, take your x value and plug it in to your function. Negative 3 squared is 9 plus 2 is 11. To find the slope, take your x value, plug it into your derivative. 2 times negative 3 is negative 6. I've got my point, I've got my slope, point-slope form. Y minus 11 equals negative 6 times x minus negative 3, or x plus 3. And that's it. All right, before we dive into AP problems, I want to talk about differentiability real quick. In other words, what are the criteria for a function to be able to have a derivative, to be differentiable? Well, a function has to be continuous, it has to be smooth, and it has to have no vertical tangents. And quickly, I've got some examples or non-examples for you here. This top graph has 2 points where it's not continuous at the hole and the jump discontinuity. The absolute value graph has a sharp turn. That's called a corner. If you have a graph that comes together not with straight lines, that's called a cusp. And this third graph has a point with a vertical tangent line. So those are all instances where a graph is not differentiable. Now, it can still be differentiable everywhere else, but at a point that's not continuous, that has a sharp turn or a vertical tangent line, it's not differentiable at that point. All right, 2008 AB number 23. This is actually a pretty tough problem. The graph of the even function y equal f of x consists of 4 line segments. Which of the following statements about f is false? A, the limit as x approaches 0 of f of x minus f of 0 is 0. Well, because f of 0 is 0, this statement is true. Answer choice B, the limit as x approaches 0 of f of x minus f of 0 over x equals 0. Now, if I try direct substitution here, I'm going to get 0 over 0. Something a little bit weird here, so let's come back to this. C, the limit as x approaches 0 of f of x minus f of negative x over 2x equals 0. Again, direct substitution gives 0 over 0, so let's save this one for last. D, the limit as x approaches 2 of f of x minus f of 2 over x minus 2 equals 1. So what you need to recognize is that this is the limit definition of derivative at a point. In other words, what's the slope of this graph at 2? Well, at 2, I can see the slope is 1. So this is true. And E, limit as x approaches 3 of f of x minus f of 3 over x minus 3. Well, again, that's the limit definition of derivative at x equals 3. And at 3, I see a corner in my graph, so it's not differentiable. So the derivative does not exist. That's also true. So how do I differentiate between B and C right now? I can see that B is the limit definition of derivative at x equals 0, which because of the corner, I'm tempted to say that that derivative doesn't exist. Well, that's true. It doesn't exist. B is actually the correct answer. But what about C? This is what makes the problem so difficult. Because this is an even function, f of x minus f of negative x is 0 no matter what. So for values of x very, very, very close to 0, the numerator is exactly 0. The denominator is a very, very, very small number. And 0 divided by a very, very small number is 0. So this is actually true. So the false statement is B. 2008 AB number 78. For time greater than or equal to 0 hours, h is a differentiable function of t that gives the temperature in degrees Celsius at an Arctic weather station. Which of the following is the best interpretation of h prime of 24? So the important thing to remember when we see h prime of 24, we're talking about derivative here, is that the derivative is the instantaneous rate of change. So if t measures hours, h prime of 24 is going to be the instantaneous rate of change at the end of the 24th hour. And so when I look at my answer choices here, A and B don't mention a rate at all, just a net change, which is not what derivative is. C talks about an average rate. Now, average rate is something else. Derivative is instantaneous rate of change. So C is out. D and E differ only in when we're looking at the rate of change. D says the end of the first day, but we plugged in 24, which we're talking about the 24th hour. So the answer is E. 2008 BC number 79. If f is a differentiable function such that f of 3 is 8 and f prime of 3 is 5, which of the following statements could be false? So this is kind of tricky. That means 4 of these must be true and 1 could be false. Answer choice A says the limit as x approaches 3 of f of x equals 8. Well, because this is a differentiable function, I know it's a continuous function, which means the limit has to exist at 3 and it has to equal 8. So that is definitely true. B, the limit as x approaches 3 from the right of f of x equals the limit as x approaches 3 from the left of f of x. Again, I know f is a continuous function because to be differentiable, it has to be continuous. And this means that the limit exists at 3. So that's definitely true. C, the limit as x approaches 3 of f of x minus 8 over x minus 3 is 5. What we need to recognize right here is that this is the limit definition of derivative at a point, specifically at x equals 3. This is f of x minus f of 3 over x minus 3. So is the derivative at 3 5? Yeah, it is. So C is absolutely true. D, limit as h approaches 0, f of 3 plus h minus 8 over h equals 5. Okay, this one's a little bit tricky. This is the limit definition of derivative, but we've substituted 3 in for x. So this is the limit as h approaches 0 of f of x plus h minus f of x over h, but we've substituted in the 3. So this is f prime of 3, which again equals 5. This must be true. I have a feeling E is the right answer. Limit as x approaches 3 of f prime of x equals 5. So why is this a statement that could be false? Because we know that f is a differentiable function. We don't know that f prime is a differentiable function. That would be an assumption. So this could be false. Not saying it is, but it could be false. 2008 BC number 89, the figure above shows the graph of a function f, which of the following has the greatest value. All right, well, let's look. F of a, so the y value that goes with the x value of a, that's a negative number. F prime of a, the slope of the tangent line at a, so this slope right here, for now we'll just say that's a positive number. C, f prime of c, so the slope of the tangent line at c, that looks pretty flat to me. If it's not 0, it's pretty close to 0, so we're going to say roughly 0. D, f of d minus f of c, so this value, this y value minus this y value is going to be a negative value. And E, f of b minus f of a over b minus a is the slope connecting point A with point B, which would be another positive number. So if I'm looking for the greatest value, I can narrow my choices down to B or E. What is bigger, the slope of the tangent line at A or the slope of the line that connects A and B? And if you eyeball it on your graph here, the slope of the tangent line at A is slightly steeper, meaning that value, f prime of A, is the largest. And last one, 2012 BBC number 11. Let f of x be the square root of the absolute value of x minus 2, which of the following statements is true. To do this problem, you really kind of need to know what this graph looks like. If you imagine for a second that the absolute value bars weren't there, the square root of x minus 2 looks like that. And there's no graph to the left of 2 because you can't take the square root of a negative number. But now that the absolute value bars are there, this is now defined for all real numbers. And the graph is a reflection. It looks like that. So what I want to point out to you is that at this point right here, this sharp point, we have a cusp, which means the graph is not differentiable at that point. And if you look at answer choice A, f is continuous but not differentiable at x equals 2. And that's exactly right. The function's continuous everywhere, but it's not differentiable at the sharp turn. So A is our answer. So to recap, to find the slope at a point, or the instantaneous rate of change, or the slope of the tangent line, they're all the same thing, called the derivative. We took our slope function and used a limit to get 2 points infinitely close together to find slope at a point. So the limit definition of derivative, the limit as h approaches 0 of f of x plus h minus f of x over h is how we find the derivative for any value of x. We learned what it takes to find the equation of a tangent line. We need a point and a slope. And we learned what it means to be differentiable. To be differentiable at a point, a function has to be continuous, smooth, and no vertical tangents. A lot of information today, but also super important. Okay, I hope that helps. Thanks for watching.